What are you going to do with the recording next semester? Or I'm not in any of your classes.
Well, I have to do it. This is I sometimes feel this is misuse of student labor in a sense. I have heard this very bad stories of in 1980s in India. They used PhD students to do their work at home. Wow. That's, I think it goes with the uh, if you search what is called Gurukul, like Guru means an instructor. So are you guys aware of Gurukul?
Yeah.
It's like Sanya with
We are aware with that.
So this is an Indian traditional thing. So
That one is even over here. I guess it's still over here.
still there?
Yeah.
In not in academics, right?
It's like for the Sanskrit. For the
Yeah, more
Sanskrit,
religious.
yeah, those kind of things they have still group.
Yeah.
I think in India, in Nepal, they are still. This time, I guess recent 5-10 years, those become like a professional.
Correct. So basically, the idea is that you have a disciple. The disciple lives with the instructor, or like at the age of 5 or something, he goes and meets the instructor, and he's he spends his life with him for the next maybe 12 or 15 years. So it's almost like a kid. So, and that tradition is called Gurukul. That basically you live with the instructor.
Like a hostel?
Like a?
Like a hostel.
I don't know.
Like a hostel?
Oh, hostel. Yeah. Yeah, hostel still is. You're
They
independent.
can come back in 1 year.
Here, you're pretty much like a kid that you live like family. So due to that reason, the instructors are respected a lot. It's almost like parents. The students treat them like
There's only one place in the States that I think does something similar to that, and it's a college. And like all this, it's a like supposed to be the most selective college in the United States, like really low acceptance rate. And all of the students and the instructors just live together in a community. There's no actual like campus buildings or anything. Like it's just a community learning environment. It's kind of weird. Seems a little cultish. I don't know. It seems a little unsettling, to be honest.
Yeah. I think my view is that it can work both ways. If the instructor is perfect, then it is good. But most of the time, or almost always, instructors are not perfect, and then you're stuck with that choice. It's probably not best.
I think in Buddhism,
Uh-huh.
even they
That's
have monk, I guess.
Yeah,
they have those
that's
things.
correct. That's correct.
They keep inside, and then they have different culture. Like from outside, they have totally different. Like they put their hair, and then their red clothes, everything red.
Yeah, I do.
Searching for peace. Searching for peace.
Searching for peace, yes. Sure. Good point, yeah. Missing few people, right? Any idea about Ian and
Ian's gonna be late. His brother's car is messed up, and so he's having to try to help him get it fixed. So
yeah, he's the go-to
car guy.
Yeah. Who's that? Oh, who's gonna meet? Yeah, that's fine. Don't have to call. Okay. So that was a homework due today. I haven't posted the homework, new homework yet. So homework 11. It will be due after thanks. Evening break. I haven't decided on the date yet. So final exam. Thank you. And we agreed on a breakfast or lunch. And this is optional. So you don't have to be attentive if you don't have to. Anything else I should pick up? Where exactly on December 12th we can decide later, I suppose.
We can decide after completing.
Okay. We started on working on the addition theorem last time, and I did not finish it, but it's an important enough relation that I think I should go through it. And it also serves as a review with what we did earlier. Remember again that orthogonality condition and completeness relation played together in a symbolic way helps a lot in doing many of the calculations that we are going. So let me recall first. So we want to do addition formula. Well, spherical. It is similar to the addition formula in trigonometry. You have, if you have two angles, sine of theta 1 plus theta 2, you write it as trigonometrically sine theta 1 cosine theta 2 plus cosine theta 1 plus sine theta 1. Similarly, in terms of spherical harmonics, you can write a similar identity, and that's what we want to go through here. First, let's begin with what spherical harmonics are, right? So it's defined using vectors A, null vector A. So we say that there exists a vector whose square is 0, which is very rare on a real space. That's not possible. In a complex plane, that is possible. And in rectangular coordinates, let's say this is, we said A plus IA2 is y minus, right? So it is minus y minus y plus. So that's the I component. Then we have y minus square plus y plus over 2 times I, and there was y plus. Like remember, we defined A1 plus IA2 as minus y minus 1, and A1 minus IA2 plus y, the 3. Think so. So there was a minus, right? I guess earlier also. I think that's what we had. And our radial coordinate, the unit vector, is sine theta cosine phi, sine theta, sine phi, and cosine theta. That's your point on a sphere. Whenever we say r hat, that does not depend on where you are in the space, so it is easy to think of it as a point on a sphere. We said that the generating function for spherical harmonic is conveniently written in terms of a dotted with r hat over L factorial. This is equal to m is equal to minus L to plus L. I'll write this in this form. Minus L m. So the understanding is that this is a polynomial and collect the powers in this form. And the coefficient is what is defined as the spherical harmonics. And that is a factor of 4 pi over 2L plus 1. That's a normalization constant that you. If you were to explicitly do this, this expansion can be done. We did that, and we showed that YLM theta phi in an explicit form. So this is all you need. Whatever I'm going to write here, that is all you need to need when you think of spherical harmonics, and it is equal. I think first try to provide the 4 pi plus 1 or 4 pi. That's a normalization constant again. Raised to pi 5 sine theta raised to m. That's your expression. It is good to see that. Let's see. Yeah, we will need this in a moment. So let's think of what is YLM, like just as an exercise, 5 exercise. We will need this soon. So let's say YLM 0, 0. Like I earlier said that this expression is all you need, but sometimes it is easier to go start from the scratch and start over, because this expression, if you were to put theta equal to 0, it may not be obvious to evaluate. Instead, if you go back in here, so if I ask you what is this, go back in here when you put theta and phi equal to 0. So if I were to put theta and phi equal to 0, so r hat in that case is equal to, if I put theta equal to 0 and phi equal to 0, what is r hat? It's 0, 0, 1, which is z hat, right? So it is right on the north pole itself. And that seems to suggest that I should be able to do this very easily, this expansion. So A dotted with z hat raised to L over L factorial is equal to, what is this? Instead of writing this as a sum, what is A dotted with z hat? We can do that immediately. That's just y plus y minus. So this is y plus y minus raised to L over L factorial. If I want to read out what my YLM is, I have to write this in this form. So I will explicitly write this as y plus to L divided by L factorial square root, and y minus raised to L factorial square root. You notice that only the m equal to 0 term is contributing in here. So this is only m equal to 0 term. So if you were to read out, so if I were to write this as a sum, I want to write this as a sum running from m is equal to minus L to plus L, then you would say plus is to plus m So I have introduced a lot of terms in here, but all of them has to be 0 except when m is equal to 0. All of them has to be 0. So this is let's say y m 0, 0. times 4 pi over 2L plus 1. So if I were to write this in this form, I immediately read out that YLM 0, 0 is equal to, it is 0 if M is not equal to 0, and it is equal to 2L plus 1 over 4 pi if M is equal to 0. So that's just reading it out. So that is what I meant to say, was that instead of always using this, you should be prepared to go back and start from the scratch sometimes. Okay, so that's a summary of your spherical harmonics, and there are also what is it? The completeness and orthogonality conditions. So let me write that on the side so that I can erase it if I need to. So there is completeness relation, and that is YLM YLM beta prime Y prime. So this is star. Remember, whenever you have unit vectors, if you combine unit vectors in the form I have, if you're in 2 dimensions, plus j hat, what is that equal to? That's equal to 1, right? That's the idea of completeness relation. That means I can multiply any vector with a 1 and get its complement. Same thing with any 2 unit vectors. This is also 1. This is polar coordinates, right? Cylindrical polar coordinates. That's completeness relation. So this is your unit vectors with the labels Lm. So I have a sum over all L's. So I have sum, right? Sum over all L and sum over all M. And that's equal to, instead of 1 now, since it is a continuous parameter, I get delta of theta minus theta prime and delta of phi minus phi prime. And that is a scale factor of sine theta in the denominator. So that's the completeness relation exactly in the form we have for unit vectors. Orthogonality is like saying I dotted with I is equal to 1, I dotted with j is equal to 0, and j dotted with j is equal to 1, and j dotted with I is equal to 0. So unless they are the same vectors, it is equal to 0. The same condition works for, if you imagine this to be your unit vectors, same thing holds. So you say YLM beta phi times it's star, and notice if it is the same, correct? The labels are LM. So now I do L prime, M prime, and the angles remain the same, the parameter on which you're integrating. So this is equal to, write this as d theta sine theta d phi 0 to pi and 0 pi. Often this is written as a solid angle. So you say this is integrated on a solid angle. That means basically you're integrating on the surface of a sphere. This will be equal to, if their L is the same, similar to here, if I is exactly the same as I, then it is 1. Otherwise, it is equal to 0. So here it is delta of L prime times delta of M prime. Okay, so that's your 2 conditions we will need. What we were working with is that we know that for a point charge, so let's say point chart. Rho of R is equal to Q times where R prime here is the position of the chart. Where you keep the chart is your R prime. Maybe I should specify position of chart. The electric potential due to this is Q over 4 pi epsilon naught 1 over R minus R prime. Let's write this as a let's write this as Q over epsilon naught is equal G of R prime is equal to 1 over 4 pi times prime. Main idea being that even though we are talking in terms of physical for intuition, we are having a point chart, but this is mathematics. We are not doing, not necessarily doing physics here. So the statement is that Laplacian satisfies the following equation: G R comma R prime is equal to Is that clear? That's because Maxwell's equations tells you this, right? Maxwell's equation tells you that electric field is negative gradient of phi, and del dotted with E is equal to rho over epsilon naught. So if you put this together, it means that the 1 over R potential has to satisfy this. And we were trying to solve this explicitly, and that will be used to evaluate what addition theorem is. But so we are practically starting from here and assuming that, or using the fact that this satisfies this function is a solution to this equation. Write this explicitly. The Laplacian in spherical coordinates it's the following: 1 over R squared by theta and acting on G is equal to delta Q. So I wrote this symbolically. You should fill this out. This is a function of two vectors. Well, let me explicitly write this down. We did most of this last time. So this is R theta phi prime theta prime phi prime. That's the 6 variables it will depend on. There is an R and an R prime. How far you are from the origin, how far the other is from the origin. But in theta phi alone, I can expand it using spherical harmonics, right? Any function in theta phi, like it's like a vector, you can expand it in terms of spherical harmonics. So I will do that. So expansion is Lm. So this is L equal to 0, infinity, and M equal to minus L to plus L. And whatever the coefficients are, this is YLM theta phi. So I've used up these two quantities inside the unit vectors, and in turn I have if you want Fourier component, are here spherical components L and M. And what are the coefficients associated with it? That I will call it Lm. But what will it depend on? It can depend on R, it can depend on R prime, it can depend on theta prime and phi prime. And the theta and phi dependence is contained in the L and M. It is like it's in the components instead of the vector. I'm thinking in terms of its components. So theta phi dependence is contained in Lm, and rest of it is kept as it is. Our goal then is to find GLM. So that is our substitute this in here, since I know how the differential equation acts on YLM. So let's recall. So there's also a differential equation for spherical harmonics, and that is 1 over sine theta, theta, sine theta, plus acting on y m. It gives you minus L such a differential equation. If I substitute it back in here, let me do this slowly in a couple of steps. Make sure you realize that most of the algebraic manipulations are sort of straightforward in this, whatever we are doing, but the conceptual manipulations are bigger in the sense that we are using the ideas of vector space. Plus 1 over r squared. Yes, theta. And it's understood that all the parameters are here. I just suppressed them to save some space. What is that equal to? That's equal to delta function, but delta function has two pieces. Yeah, let me write this down here more explicitly. So this is r minus r prime. So this delta function, we have three delta functions in here. So that's delta of theta minus theta prime, delta of phi minus phi prime, and that is r squared, and that is sine theta. That's the volume element of a spherical or a small cuboid, if you want, in spherical coordinates. So if I were to use this is equal to delta r minus r prime over r squared. Use the completeness relation to replace that. L m y m theta phi y m theta prime phi prime. Is that clear what I did? Mostly using ideas of a vector space. I'm not really algebraically doing anything. Any questions? Okay. Now, if you have two vectors which are equal, that means their components has to be the same. If two vectors are equal, then the components are the same. I can bring out the sum here. These are the unit vectors, and these are its components. So this equation must be true for any Lm. true for each L M. That's because these are components of a in the spherical harmonic space. If that is the case, I can make this operate on that. So this is 1 over r squared d by dr plus 1 over r squared. This acting on YL and theta phi, that gives me G minus L times L plus 1 itself. And G M. And on the right side, I will be taking only one of them. Whatever is remaining is delta of R minus R prime over R squared times Y M theta prime. The thing. So I sort of read out like what is the coefficient of YLM here should be equal to the coefficient of YLM here. So I'm pretty practically reading out what the components are. And that immediately gives me a differential equation now in a single parameter. Usually partial differential equations are much easier when you have only one differential operator here. And if we can solve this, I practically get my coefficients. These are my coefficients. That was my exercise, that how can I expand this in terms of GLM. That was the exercise I'm trying to do. So if I solve this differential equation, I'm in a sense home. There's a simplification here. There's R squared, R squared, R squared that I can cancel out. So let's do that. Right. R squared, R minus of tau plus 1 E M. There is one thing you can immediately see, that everything here is on R. So theta prime, phi prime, it completely separates out. If you want to separate it out right there, it is okay. But let's keep it here. You don't lose much by keeping it there. So that's a Green's function equation. Whenever we have a Green's function equation, and by Green's function, I mean this right-hand side contributes only at one point. When R is equal to R prime, it is 0 almost everywhere except at one point. So use that fact, recall. So if R is not equal to R prime, then we have d by dr times R squared times d by dr times G M is equal to L times L plus 1 times GLM. So that's a differential equation you have, and you immediately see that if GLM was of the kind R raised to L, then d by dr R squared R raised to L would be equal to, so you first take L times R raised to L minus 1, then you add a plus 2, and then you again differentiate, you get an L plus 1 this time, and then you subtract 1 again, so that's equal to L into L plus 1 times R raised to L. So that surely satisfies that equation. You can also try GLM and 1 over R raised to L plus 1. And you will see that again it satisfies. So this is d by dr 1 over R raised to L plus 1. This one now is minus of L plus 1. So we write it as R raised to minus L plus 1. Then you have, so I'm doing it here, right? So it is minus and then R raised to minus L minus 1 and minus 1 again. And then I have to do plus 2. That's R squared, and then differentiate again. Now it is just minus L that comes out, and I subtract it again. So this is equal to L into L plus 1 times R raised to L plus 1, I suppose. So you can verify that both these satisfy the Green's function. Whenever you have a solution, one satisfied on one end of the range and the other satisfied on the other end of the range, that's an indication that these are two independent solutions. So that means GLM can be written as some coefficient times R raised to L plus B times R raised to L plus 1. And this is R comma. Okay. And we have to find A and B based on physical requirements that what are these conditions. And remember, R here, R and R prime both, R is less than infinity and greater than or equal to 0. These are spherical coordinates, right? So they cannot be negative. So we call so we are talking about 0 to infinity instead of minus infinity to plus infinity. When we are thinking of Green's function, this consists of two pieces. That is an R equal to R prime, and so this is your R equal to 0. So this is R, and that's infinity, and somewhere here is R prime. R prime can be thought of as a fixed parameter. So at some point R prime, there is a source, if you want, which contributes at the right hand side. That means the solution that we have written will have a contribution from here and a contribution on the other side. So GLM then can be equal to A times R raised to L plus B times R raised to L plus 1 for R less than R prime. And when it is on the right hand side, it's a completely independent solution. I don't have to have the same coefficients at all. So it can be C R raised to L plus D R raised to L plus 1. Recall your Green's function analysis that we were doing earlier. The only difference being that earlier we were doing for exponential functions or sine and cosine. Here they are in powers of L. Now put in the requirement. Here we are doing the solution for the Green's function due to a point charge. We would like it to be not infinity. The electric potential should not be infinity, right? At R equal to 0, or for that matter, at R tends to infinity. Remember, the point charge is here. Right? This is the point charge. So the potential can be infinity right at the position of the point charge because it is 1 over R minus R prime. But you don't expect it to be 0 at the origin. Right? Remember, this is spherical coordinates. This is the whole space. This is only the radial coordinate. So again, so this is your origin. So that's your R prime. That's your vector R prime. That's where the point charge is. Because there is a point charge there, electric potential here should not be infinite at the origin. Origin is a harmless point when you're talking about a charge at R prime. Same thing at infinity, it shouldn't blow up again. So you require that at R equal to 0, GL should not blow up. Should not be infinity. Which means that you cannot have B here. So that implies that B is equal to 0. That's a physical condition we are putting, that at R equal to 0, GLM is finite. That means it can be as large as you want, but not infinite. It shouldn't blow. It can be a large number, but not infinite. Same thing at R tends to, as R tends to infinity, GLM should tend to 0. And that means, that implies that C should be equal to 0. That's just physical conditions. And then immediately we say that GLM, I've used up all my physical requirements, and now I'm completely in the Green's function equation alone. So this is equal to A times R raised to L, or R less than R prime. And here I have D over R raised to L plus 1, or R prime less than R. So I have an equation for Green's function. This I could have immediately concluded, and I know that these are my solutions, and there are two regions. This solution is applicable for R when R is less than R prime, and the second part is applicable for R greater than R prime. And how do we fix these two conditions? Always, in a Green's function, there is more information. Because there is a delta function on the right hand side, there is always more information in the equation. That is what is called continuity condition. So now we can derive continuity condition from this equation, and that will let us calculate our A and D. Notice the continuity conditions are part of the differential equation. Its initial conditions are different. They are given by the problem. Like these are initial conditions or boundary conditions. Like that was a physical requirement that my solution has to be 0 or it should be finite. Those are all physical requirements. This is contained in the equation itself. Equation itself tells you what my A and D is going to be. So let's do that. Let's try to get the continuity conditions for that equation. So continuity conditions. And this has nothing to do with addition formula. This is a property of Green's function, but this is a review in that case. So whenever you have a delta function, we know that the integral of a delta function is 1. So trick or an idea, the idea that we use for continuity condition is that if you have an integral of, let's say, delta of x, that's equal to 1. And I only have to go from 0 to epsilon and 0 to plus epsilon. As far as I go at the point where the delta function is, if I go around that I will also always get 1. I can also do minus infinity to plus infinity. That is what we usually write. But as far as I capture that peak that I have, I will get that to be 1. So let's do that for this equation in here. Let me evaluate this integral on R. So remember, I have my R is 0, and that's R prime. So let's evaluate this from R prime plus epsilon, and this is R prime minus epsilon. So I integrate on that small region of space. This is R equal to R prime minus epsilon, and R equal to R prime minus epsilon. Is that clear what I'm doing? Do that integral. So this is R prime minus epsilon. This is R prime plus epsilon. This is d by dr squared d by dr and GLM. That's the first piece. And the second piece is plus L times L plus 1 times an integral r prime minus epsilon r prime plus epsilon, and that is GLM is equal to the integral of this, since r prime is in between that, r equal to r prime is in between that integral, that will be equal to 1, and whatever is remaining is YLM theta prime I prime. With me? This is a total differential, so this will contribute only at the boundary. Like fundamental theorem of calculus, integral is the anti of derivative, only the boundary contributes. So this is minus r square d by dr of GLM. I have to evaluate this at 2 points, upper limit and lower limit. So it's r equal to r prime plus epsilon and r equal to r prime minus epsilon. Remember, GLM had 2 parameters, right? R and r prime. We are doing this evaluation at r. So if I evaluate r equal to r prime plus epsilon, then subtract it r prime minus epsilon. What is happening there is that the 2 solutions here, when you're doing the plus, it will be on the right side. So then this solution contributes. When I'm doing it on the lower side, this solution contributes. So this is kind of a patchwork we are doing. We have 2 solutions. How do they combine together at the boundary? That's why they are called continuity conditions. So we are saying that the derivative of these coefficients of these solutions has to satisfy this equation. That is this piece also. So L into L plus 1 and then ER prime minus epsilon or prime plus epsilon GLM is equal to YLM theta prime of phi prime. Now, if we have to proceed, I have to somehow argue what my second term is. What will this integral be? Second term?
0.
And why is that?
It's continuous on an infinitesimal region. And so since that region goes to 0, you should get 0 as your result.
That's correct. What about the derivative? So is this function, so notice GLM, that's a correct argument, completely correct. So if I were to plot so let's say this is GLM. So that's one possibility, that this is the functional dependence in here, and that's R prime. And we are taking the area of this in this region. Right? This is R prime plus epsilon, R prime minus epsilon. And if I take the limit epsilon tending to 0, this area will go to 0. But if GLM was of this kind, it will not satisfy the equation because this is continuous and its derivative is also continuous. We are just seeing that the derivative is not continuous, right? It is supposed to be so on. So this is not a true description of this feature here. So this could be like this, and or maybe better. So let's say this could be like this, and so notice here now, or again, the derivative is not continuous. Right here, derivative is not continuous, but still, if you take the area, that still goes to 0. One might wonder, there are many other possibilities, right? Why not this? Right? That's also a possible G. Right? That's your R prime. And now the function itself is discontinuous. Why is this not allowed? Why can't I have a G of this structure?
Beginning of your approach, you have different values. That's all.
Try that again, clear?
As you take that epsilon smaller and smaller from one side, you'll have a different solution from the other side.
You have to get the.
But
I'm not able to hear you.
I'm saying
Be louder.
as like from the right side, as epsilon comes in, you'll have one solution. On the other side, you'll have a different.
Yeah, but what's wrong in that? Like if we are doing physics, I have a conductor, I get the electric potential on the right side, I have the electric potential on the left hand side. They can be different, right?
Yeah.
A priori, ad hoc, at some level, we can say that that could be different. But mathematics is supposed to guide us as to what will be the solution. So there is nothing wrong in this solution, but notice what we are having. If, like, let's begin with the statement that our solution is of this kind. If this is the solution, what will be its derivative? What will be the rough derivative at this point?
Infinite.
Again?
Infinite.
Infinite, right? Very good. So this will be a delta. So if this is a step function, as we have, its derivative will be a delta function. Second derivative will be a derivative of a delta function. Right? So second derivative here is not s derivative of a delta function. I want a delta function. So this already rules out those kind of solution. But it also tells us the solution must be of this kind because I want a delta function anyway. I don't want a higher order delta function, but I do want a delta function. So Green's function sort of says that somehow the continuity conditions should come together so that this is equal to YLM. Now, what we are not keeping in here is that now what I'm going to say is that this is exactly equal to 0. That's not necessarily true because you can have a linear combination of that. And that is indeed possible. And there are various Green's function solutions you can have. They are called Robin boundary conditions. So that's all possible. But we will take the simplest scenario that this is equal to 0. That's perfectly okay, this part. Okay. So so if we want to satisfy this, so continuity condition will be one is that this is equal to 0. So that means GLM evaluated on the positive side and subtracted from the negative side is equal to 0. That means this is really continuous and its derivative has to be discontinuous and not just discontinuous, it has to satisfy a specific value. M plus to minus, by plus and minus I mean from the right side to left side, that's equal to YLM eta prime by prime. Okay. Put these things in this equation or this values in that. This means that the right hand side, which is d over r prime raised to l plus 1. Like remember, we had to substitute r prime. And minus of a times r prime raised to l has to be equal to 0. If that's the condition we have. Is that clear? Right. My solutions are, this is on the right, this is the positive, and that's a negative, right? Positive means on the right side, on the negative on the right side, on the left side. So this minus this has to be equal to 0. And the second condition is first I have to take the derivative, right? So let's do the derivative there itself, maybe. Yeah. So here, derivative of G Lm over R. This is equal to A times L times R times L minus 1, and the denominator will be minus D L plus 1 times 1 over R raised to L, I suppose. No, L plus 2, I guess. Is that correct? Right, that's your less than R prime and R prime less than 2. substitute this in here. And we have this 1 over r square also, which I have to keep track of. So this is minus of that. So it is d times L plus 1. And then r squared. So this is r raised to r prime raised to L. Is that correct? I think so. Minus of this evaluated. So minus and a minus becomes a plus. So it is a times L r raised to L plus 1. And I think I made a small tiny error here. There was a, I think when I wrote this down here, the continuity, or sorry, the completeness relation had a star there, right? There was a complex conjugate there. So I'm going to correct this here. This was a complex conjugate there. So we got that. Sorry for that, right? And that will go in here, here, and that will go in here, and that will go in here. That's two unknowns and two equations. I can solve for that. So first of all, let's do d maybe, right? So d is equal to this times this, that is L. Also in the denominator I have L, and then minus and a minus plus of prime cancels out, and that is an L plus L plus 1. And that's 12 plus 1. In the numerator, when I'm solving for d, I substitute this in here. So it is 0 and YLM. So it is R prime raised to L times YLM theta prime 5 prime star. So that's equal to L prime L plus 1. And A similarly would be equal. Well, for A, this comes in there. So this is this times this. You have 1 over 2L plus 1. 1 over R prime raised to L plus 1. That's all for A and D. Is that clear, the process that we used any questions here? So at this point, I have practically solved for my GLM. And once I have GLM, I can substitute it back somewhere here, and I will get my complete width function. Okay. So let's do that. So I think I will go to the right side and so GLM is dependent on R prime, theta prime, phi prime is equal to, it has two solutions, one for R less than and one for R greater than. When it is less than R prime, it is A. So that's equal to 1 over 2L plus 1. That is R prime, R raised to L, and R prime raised to L plus 1. And that is Y M prime prime. This is when R is less than R prime. And if it was The other side, D, do the same thing. 1 over. This is R prime. It's L. And R raised to L equals 1. And you notice that, oh, there's a star again. Prime, prime. So, and this can be captured in our notation. One is it is symmetric in R and R prime. So this is the same as 1 over 2L. 1 over R greater, whichever is greater, or less, or R greater. L. That's GLM. So my solution here for the Green's function, if I substitute this in, I have my solution. Remember my Green's function. Remind ourselves again. So this is this was 1 over 4 pi times 1 over R minus R prime is what we call the Green's function. It's equal to L equal to 0, infinity, M equal to minus L plus L, and we expanded in spherical harmonics, and these are the coefficients we have got. So put that in Y, L M, Y, BLM is, let's write this explicitly, so 2L plus 1 over R greater. Put the 4 pi's in the on the left hand or the right hand side, and we learn that 1 over R prime is equal to, let me rewrite this or just rearrange this basically. L equal to 0 to infinity, so the 4 pi over 2L plus 1. And keep the L order of everything outside the M integral. So that's a very important relation in spherical harmonics. Remember, this is your electric potential due to a point charge, the Green's function, if you want. This is the expansion you have in terms of spherical harmonics. It plays a very significant role in almost every calculation that you will use spherical harmonics in. But we said we are interested in addition formula, right? Yes.
First YLM, there's a theta pi only.
That came up. Good. Yeah. But I said, I promised that there's going to be an addition formula. Yeah, there is a sum of quantities, but you have to have a single angle sum, all right, theta prime plus phi prime. I mean, for that, go back to your legendary polynomials. We also have another expression for this, right? And we said that this is also equal L equal to 0 to infinity 1 over R greater. What is that equal to? The rest of it,
The elf was on the polynomial
is out of
cosine theta.
of cosine theta, correct? So remember, r and r prime are two vectors. So what we are saying here is that r prime is equal to z hat. Or let's say is equal to r times z hat, r prime times z hat. Because r prime is still there. No, r prime is r prime is equal to r prime times z hat. That immediately tells me that r dotted with r prime, r dotted with r prime will be equal to r prime times cosine theta. It's still within the screen, hopefully. And that's what gives you this cosine theta feature in there. But here, that restriction is not there. If this is in general, r and r prime could be anywhere. But when we said r prime is along the z-axis, and r is somewhere here, and that's your angle theta. If I were to move this around, earlier we also said that if I were to choose cosine gamma is equal to cosine theta prime plus sine theta prime times cosine of phi minus phi prime. If I rotate this off, this is what I would get. So this is also true. So make this more general, and this would be cosine of gamma. Even though when we were deriving it, we choose r prime to be along the z-axis, but if I were to rotate it, the only thing it depends on is the angle between r and r prime. So that's the only quantity that comes out. And that gives you, if I now compare these two, that gives you the addition formula. Let me write that down there. Yeah, let me serious. Addition formula. Or spherical harmonics is comparing these two. This goes away, L sum goes away, so I have PL, Legendre polynomial. The sine of gamma, I tell you what this let's do this is equal to 4 pi over PL plus 1 sum as the sine gamma. So if you have your coordinate system somehow like this, vector r, that's your r prime, that's your gamma. This is theta phi, that's theta prime phi prime, and gamma is the angle between them. And you can show that this is equal to cosine theta. That's just r dotted with r hat, dotted with r hat prime. So this seems like it is pretty convoluted, right? There is a theta and theta prime coming together in such mixed form, but the sine gamma can be separated into theta and phi. The theta dependence and the phi prime or the theta prime dependence, the angular dependence completely separates out, and that's why it's called an addition formula. Think of sine and cosine sums. That's practically the double angle formula. But here this is multiple functions that is contributing to that. I'll stop here. There is 5 more minutes, but don't want to start. I think at this point. Yeah, quiz. I should give you a quiz, right? Write this down for L equal to 1. And if you get L equal to 1 is the only part that is needed for quiz. But if you get curious, go ahead and do that for L equal to 2 also. It's tedious, but at the same time, you see a pattern. Like again, these are solutions to angular momentum, so that is physical significance for this function. Hydrogen atom solutions are given in terms of spherical harmonics. So whatever you do, probably unless you're doing very elementary stuff, you cannot escape this. Stop here. Okay.
So there should be some theta, right?
Oh, did I miss something?
The last line.
Yes,
Yeah.
time data prime. Yes, thank you.